No, this one only, no?
That means that it's bounded above. Yeah.
This is bounded above that, you can do it.
I'll try it.
Because what you need to do is 1 plus 1 over n raised to the power n is 1 plus n times 1 over n plus 2, yes, n times n minus 1 divided by factorial 2, that means 2 times 1 times 1 over n squared plus and so on, plus 1 over n raised to the power n. So this is like 1 plus 1 plus you can do it, I'm sure. Make it less than or equal, less than or equal. Then you get, this is, I guess, less than or equal to 3. You can prove easily. This is 1, this is, then you get, this one is 1 over 2, no? Plus, I guess, if you write next one 2 square, and so on 2 to the n. This is then strictly less than. This is equal to 1 plus 1 plus 1. This is, even if you add all the way, 1, this is geometric series, you get 1. This is equal to 3. Right? You need to prove, I mean, this term is very clear, no? N times n minus 1 divided by n squared is less than or equal to 1 over 2. Next one will be less than or equal to 1 over 4. Like that. It is something you can do, no? It's just a mechanical thing. Anyway, so what is important from this is that 1 plus 1 over n raised to the power n is strictly increasing and it is bounded above by 3. If you cannot prove less than 3, then you are not good, but tell me. You must be able to do it nicely. But anyway, if you cannot do it, you need to tell me. So it has a limit. To this day, nobody knows what the limit is. As a result, we call it P. Whatever we don't know, we say E, phi, gamma. We put some letters. Then we can prove that E is irrational. We proved, no? Did we?
No.
Oh, E is irrational, I guess. Somewhere. Anyway, if we haven't proved it by any chance, let's do it on another day. Then whole bunch of things to be done. And even though you didn't submit homework that I asked you to submit, he has submitted. You have to write because now he is quite good by now, but he doesn't consider all the cases. 6.4.4, let's see. Before going to that, today 6.4. What is it? 6.4.4 lemma, 6.4.30. Where is this guy? 6. Prove lemma 6.4.30. I cannot find. It is a good one. Yeah. Even though it is going to take time, it's good to do. Good morning.
Good morning, sir.
Oh, good morning, sir. He says comparison principle. Suppose A and B and these are two sequences. Well, I don't write other when going into infinity, etc. You can write it such that A less than or equal to B. Anyway, so this goes from m to infinity, m to infinity, a less than or equal to bn, for all n greater than or equal to m. You have to prove four things: sup a n less than or equal to sup b. Sup b n going into infinity, n going into infinity. We are not told that these are bounded sequences, so we have to consider that case also. In case this is first one, we need to show one thing we know for sure clearly: sup b n going into infinity is equal to infinity O. Is strictly less than infinity. One of them, let's take this one. Suppose sup b n going into infinity is infinity. If this is infinity, there is nothing to do. Then it is clear that sup a n, this thing is shown?
Yeah.
And less than or equal to sup b n, like this, because anything is less than or equal to infinity, we are dealing with real numbers. Case 2. Now suppose sup b n strictly less than infinity. Then when it is strictly less than infinity, there are two choices. One is it is a real number, other one is
It's minus infinity.
it is minus infinity. You have to prove that. You don't have to write it here. You have to show in your mind or even write a proof that it will never be minus infinity. Because of the way you write, you don't get that. Anyway, so I will take thus sup b n going into infinity is a real number. I said thus. Why? Because it cannot be minus infinity. So you have to at least explain every why, not now. Every day I think when I go to Billiandala to buy a couple of pens, every day I forget. Left. Now that's a good pen. And that's equal to sup b n to infinity. Hence, for each n greater than or equal to m, b n less than or equal to lambda. No? B n less than or equal to lambda. Since a n less than or equal to b n for all n greater than or equal to m, if b n less than or equal to lambda, then a n less than or equal to lambda right away. We have a n less than or equal to lambda for all n greater than or equal to m. So this means lambda is an upper bound of a. Sup is the least upper bound. Thus, lim sup, not lim sup, sup. A n less than or equal to lambda. I did not write that part. I may write 4. Here lambda is an upper bound. Sup n is the least upper bound. That is plus sup n, sorry, less than or equal to sup bn. I am writing. You can put n going m to infinity. This and that. So we have to clarify. We need to clarify that sup bn cannot be minus infinity. Tell me next day. Not now. I don't want to think about that now. 2, let's say. 2, let's say. Number 2, need to show that. Inf A n going into infinity. 2 less than or equal to inf bn. And see, the thing is, important thing is, if each term of the you can say n less than or equal to each respective term of dn, then sup a less than or equal to sup bn, inf a less than or equal to inf bn, lim sup a less than or equal to lim sup bn, lim inf a less than or equal to lim inf bn. This order preserves by limits and lim sups and sups. If a less than or equal to bn, if both of them have limits, then limit a less than or equal to limit bn. Like that. Order preserves. Clearly here, only on this code is focus. Now, this one, clearly, inf a n going into infinity is minus infinity inf a n going into infinity greater than minus one of them. No? That is of course true. Case 1. Suppose that inf a n going into infinity is minus infinity. Then it is no, then it is clear that inf a n going into infinity less than or equal to inf b a. Answer. Case 1 is trivial. Case 2. Now suppose that inf a n going into infinity is strictly greater than minus. Then again I am saying, if it is greater than minus infinity, it is a real number or it is plus infinity. But it will never be plus infinity. Again you have to tell me why. So next day, then it is thus inf a n going into infinity is a real number, belongs to R. Let u equals inf a n going into infinity. Hence, for each n greater than or equal to, for each n greater than or equal to than or equal to a n into 1. Since a n less than or equal to b n for each n greater than or equal to m, mu less than or equal to b n for each n greater than or equal to m. Therefore, mu is a lower bound of Bn, but then if Bn is the greatest lower bound, I'm writing that part, hence mu less than or equal to if Bn, thus if An n going into infinity is less than or equal to if Bn n going into infinity. Right? Because you in your answer, what you have written is correct, but you haven't considered these cases. Plus the other thing is, by the way, proof by, even though proof by contradiction is correct, of course it is correct for us, I told you it is not correct for the grandma. Try to, if you can write proofs without using the proof by contradiction method, that is better, because from that you may learn better. But if you write a proof using proof by contradiction, that's true, that's correct. Okay. So we are done with that. Now the third part, last part is, now let's go here. 3. We need to show that. 3. Need to show that. Linsu. An less than or equal to Linsu B. By the way, another thing is, he writes n tends to infinity here, below so. But I write n tends to infinity here. Because you take limit when n tends to infinity. You don't take sup when n tends to infinity. You take the sup of an plus 1 and so on. So that is another thing I'm thinking of writing to him. If he sends me money to eat at least a pizza from Pizza Hut for my recommendation. You see my point here?
Yeah.
This is how I write. Anyway, so he writes. Then clearly here, Bn going into infinity is unbounded above. Oh, Bn going into infinity is bounded above. One of them. Taking let's take case 1, suppose Bn n going into infinity is unbounded above. Is unbounded above. If it is unbounded above, thus we can say right away, according to his notations, thus Bn plus is what? For any n. Bn is unbounded above. Thank you. Plus infinity. You see that? It's plus infinity. For each n greater than or equal to n. Hence, limit capital N tends to infinity, Bn plus is definitely plus infinity. Actually, I don't know whether we can write limit of infinity is infinity. I don't know. So therefore lim sup is lim sup, no? This is thus not thus, that is lim sup Bn is equal to infinity. If lim sup Bn is infinity, then this inequality goes without saying, means lim sup An less than or equal to lim sup Bn, you can put parentheses in going from n to 0 or what. Case 2. Now suppose Bn n going n to infinity is bounded above. Is bounded above. Then Bn plus B capital N plus here, which is the supremum of Bn, n going from capital N to infinity, is less than infinity for each capital N greater than or equal to n, no? If it is bounded above, no matter from you begin, still bounded above. So supremum is finite. We know that. We know that an plus n going into infinity, b plus n going into infinity are decreasing sequences. Decreasing. Right, we know that decreasing sequences. They may be unbounded below. I did not say anything. Decreasing sequence, thus, but I am saying is thus limit n tends to infinity. An plus is actually increment of an plus n going from n to infinity. Decreasing sequences converge to, even if it is unbounded below. Even if it is unbounded below, I did not write that part, and limit Bn plus n tends to infinity is equal to if Bn plus n going from infinity. Now, that is my proof. If An less than or equal to Bn, we have shown that if An less than or equal to with Bn. Now, we know where am I? Hence from 2 if An plus n going infinity less than or equal to Bn plus n going from n to infinity. So, A less than B. Last one I am not doing it, it is parallel to this one. What the way you are writing is good. However, that's the big improvement. However, you always try to go to proof by contradiction. I mean, that is correct, but on the contrary, when you write this sort of proof, you see now, if you want to prove that there are infinitely primes, you use the proof by contradiction method. If you assume that there are finitely many primes, you can take a contradiction. But you don't know at least 100 primes. If you write a direct proof, if you had written a direct proof, you would have seen many primes. So proof by contradiction is a very good method. But you don't see the result. I mean, why it is true, of course. You assume the result is not true, then you run into something absurd. Then you say what I assumed is wrong. Therefore, the result is true. That is proof by contradiction method. It is a very good one. Say for instance, if you want to prove that there are infinitely many even integers, if you assume you can prove it by contradiction. You assume there are finitely many, of course, then you can get a contradiction. But if you say for any n belongs to Z plus 2n is even, so then you have proved, you have shown even what are these infinitely many even integers. So if you can avoid proof by contradiction at places where you use, that is very good. But in mathematics, of course it is correct. So I am not proving the last one here. You can prove it. Now I am proposing. I took too much of time. We have finished with some stuff. Anyway, I looked at the book I have written.
Yeah, you were gonna show that your definition of the Lipschitz method, definition of the book is the same last day.
That day, no? But I passed the Lipschitz is the maximum. Yeah. So let's see, I have to, even if I cannot finish them today, though I have 2 weeks, I have to take at least one more day. I sort of don't like to,
Rush.
oh yeah. You cannot learn maths. Sometimes when you write quickly, you may not see the relevant points now. For instance, here, I said now suppose n should be less than infinity. Therefore, n should be n belongs to R. Somebody may wonder why on earth it cannot be minus infinity. So, these sort of things are crucial things in maths. But anyway, let's do as much as possible. However, your knowledge as a person who hasn't been doing a test is very good, both of you. But you are writing that you are sort of lax. You need to write more and more. That's how you will learn. That's the only way to learn how to write. Before going to prove my definition and the definition in the book are the same, I will prove that I said that when you are given a sequence X and let's say bounded by Bolzano-Weierstrass, every sequence has a monotonic subsequence. We prove that. Using that we can conclude that Bolzano-Weierstrass theorem, every bounded sequence has a convergent subsequence. Again I added to that even if it is unbounded above, that is true, then if it is unbounded above, it has a sequence that diverges to plus infinity. If it is unbounded below, it has a subsequence which diverges to minus infinity. So it's sort of an amazing result then. Every sequence has a subsequence which has a limit finite to infinite. So then I am saying I told you, then I considered you are given if you consider LXN, that is the limits of convergent subsequences, set of all limits which are subsequential limits. That set is of course bounded above, since the original sequence is bounded above, subsequences are bounded above, limits are bounded above, bounded below all. Then I was saying that this set has a maximum. Though we call it lim sub, one can say it is lim max. So that is a very strong result. So I am going to prove that now. Let's see. I will not write all the details, but I will have to write. I will write. Anyway. No, you can take the next 10 previous to it.
Yeah.
Let's say theorem. Let me write this way, my way to save time. Let Xn be a boundary sequence. Of real numbers. When I prove this result, first, these proofs are my proofs. It was a big thrill that I could prove it. Yeah. Then lim sub Xn is equal to maximum of Lxn, max Lxn, and lim min Xn is equal to min Lxn. So I will prove the lim sub 1. Then same kind of pattern, lim min follows. Proof. Let lambda is equal to lim sub Xn. Then what do I have to prove? I have to prove that there is a subsequence of Xn, say Xnk, which converges to lambda. That's what I have to prove. Let lambda is equal to this. Then lambda belongs to R because bounded above. Bounded. We need to show that. Lambda belongs to Lxn. So far what we know is lambda is the supremum of this thing. We need to show that lambda belongs to Lxn. Therefore we need to show that there is a subsequence Xnk. There exists a subsequence Xnk of Xn such that, let me write the same substitute like in the book, such that lim k tends to infinity, Xnk is equal to lambda. I have to produce a sequence Xnk, so that there is, as I told you, analysis is difficult. One reason is this thing, there exists. Nobody knows where it is, but we say there it is. Okay. You know that for each epsilon greater than 0, greater than 0, there exists L epsilon belongs to Lxn such that lambda minus epsilon is strictly less than L epsilon less than or equal to lambda. This is by the meaning of SU. So far, lambda is the supremum of the set of subsequential limits of x. So from that, that's why I told you in this case, in the book, he doesn't go for this language. So I don't know how he can prove this result, for instance, without using epsilon. I cannot do it. And I shouldn't say I cannot do it, I don't try to do it because I don't think. So we are using this one very heavily in order to construct the sequence x and t. So I choose very important for you to catch this trick of constructing the sequence. Let's put epsilon is equal to 1/2. Then there exists L1 belongs to maybe we should send an email, Prabhas, bring books of pens. Then there exists L1 belongs to Lxn such that lambda minus 1/2 less than L1 less than or equal to lambda. Because this line is true for any epsilon. I chose epsilon equals 1/2 actually to do the 1 if you want. Epsilon this time is 1/2 to the 1. Right? This line is true, no? Lambda minus 1/2 is less than L1 less than or equal to lambda. Because L1 belongs to Lxn. L1 belongs to Lxn. There is a subsequence. There exists a subsequence x and k, x in R, I guess I have written. X in R of xn such that lim R tends to infinity, x in R is equal to L1. Right? Lim R x in R is equal to L1. Choose N1 belongs to N such that minus 1/2 is strictly less than x in 1 minus L1 is strictly less than plus 1. So I am going to now look at here. Lambda minus 1/2 is strictly less than L1 less than or equal to lambda, and I have chosen N because lim R tends to infinity, x and R is equal to L1. Yeah, so you can choose an N1, not N by the rings if you get it. Next time I will say choose N1. They will get it like this. Now can you see therefore xn1 here xn1 is strictly less than L1 plus 1 half. However, L1 less than or equal to lambda. Therefore, I can say lambda plus 1 half. Xn1. And on the other side, xn1 greater than L1 minus 1 half. And L1 greater than lambda minus 1 half. Therefore, you can say xn1 greater than lambda minus, not enough space. I should have written that first. Xn1 here greater than, I can say from here xn1 greater than L1 minus 1 half. L1 greater than lambda minus 1 half. Therefore, xn1 greater than lambda minus 2 times 1 half. Right? And the other side, of course, you get lambda plus 1 half, that's like erase. Now I have my first term of the subsequence, xn1 as the property, xn1 greater than lambda minus 2 times 1 half and other side less than lambda plus 1. Now put epsilon is equal to 1 half square over 2 square. Then you get, then there exists L2. Then there exists simple L2 belongs to Lxn such that lambda minus 1 half square is strictly less than L2 less than or equal to lambda. So I am again using supremum of Lxn is lambda. So if you subtract something little, there is a bigger element. Every element is less than or equal to lambda. Again I am using, because L2 belongs to Lxn. Now let's go. This one is difficult to erase because L2 belongs to Lxn. Lxn. There is a subsequence, there is a subsequence. Again, I have written, again xnr doesn't matter. xnr of xn such that lim r tends to infinity xnr is equal to L2. You agree with what I write, no? Again, I want to say choose n2 belongs to n. N2 belongs to binary Z plus such that first thing is n2 must be greater than n1, and time is the pens. Every day actually I thought of buying one or two pens. And minus 1 over 2 square is strictly less than x into minus L2 less than 1 half square. Because L2 is a subsequential limit of x and R. This line is correct. Then I'm going to write up about here. Therefore, you can say, can you see what I am writing? Therefore, lambda minus 2 times 1 half square plus x strictly less than x into x strictly less than lambda plus 1 over 2 square. But same argument here because L2 less than or equal to lambda, xn2 minus L2 plus than 1 half square. Therefore, xn2 less than L2 plus 1 half square, but L2 less than or equal to lambda. Therefore, right side is clear. Similarly, the left side. You can see. I will put only this line. This is the last line. Now you need to get the pattern. Now put epsilon is equal to 1 over 2 to the 3. Then there it is L3. There it is L3 belongs to Lxn such that lambda minus 1 over 2 to the 3 strictly less than L3 less than or equal to lambda. Right? You can do it. Because L3 belongs to Lxn. L3 belongs to Lxn. There is a subsequence. There exists a subsequence. Again, I am not using the same notation, it's in R of xn. Such that limit R tends to infinity, x and R is equal to L3. Now I am saying, now choose L3. Belongs to Z plus, so that L3 is greater than into and minus 1 over 2 to the 3 is greater than x in 3 minus L3 is greater than 1 over 2 to the 3. So therefore I will write, by the way, therefore you can see this thing, lambda minus 2 times 1 over 2 to the 3 is greater than x in 3 less than or equal to, no, less than or equal to, this time is greater less than, this side is greater less than lambda plus 1 over 2 to the 3. Now in my book I have said the same thing, not the same thing. How do you write? Very precise way. Let me write it because you guys have to learn to write proofs. So suppose N1, N2, Nk have been already chosen. These pens are these pens expensive?
No, we'll buy some.
Eh?
We'll buy some now.
That's really. Anyway, Nk have already been chosen. See. Have already chosen, have been chosen, have been already chosen, so that N1, N2, bingo, 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 Nk belongs to Z plus N1 strictly less than N2, strictly less than bingo, 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 Nk and lambda minus 2 times 1 over 2 to the I is strictly less than xmi plus than lambda plus 1 over 2 to the I for each I going 1, 2 up to k. This is the way, without writing, proceeding in this manner, this is the real way of writing. Of course, to understand, you can say always proceeding in this manner, but that's not rigorous proof. Now put epsilon is equal to 1 over 2 to the k plus 1. Then there it is. Simple Lk plus 1 belongs to Lxn such that lambda minus 1 over 2 to the k plus 1 is strictly less than Lk plus 1 less than or equal to lambda. Again by the definition of SUP of Lxn. Because Lk plus 1 belongs to Lxn, there it is a subsequence xnr of xn such that limit r tends to infinity, xnr is equal to Lk plus 1. Now choose Nk plus 1 belongs to Z plus such that Nk plus 1 strictly greater than Nk and minus 1 over 2 to the k plus 1 strictly less than xnk plus 1 minus Lk plus 1 is strictly less than 1 over 2 to the k plus 1. That's, you got the pattern, no? Thus from induction. No, therefore, therefore, lambda minus twice 1 over 2 to the k plus 1 is strictly less than x in k plus 1 is strictly less than lambda plus 1 over 2 k plus 1. So now I have chosen for every k I have this sequence xn k lies between lambda plus 1 over 2 to the k plus 1 and lambda minus 2 to the k plus 1. Now I am done actually. So let me write this. Thus by induction, thus from induction, because you need to write thus from induction. We have a strictly increasing. We have strictly increasing. Increasing. Sequence. Sequence. NK of integers. Such that for each k belongs to Z plus, lambda minus 2 times 1 over 2 to the k plus 1 is strictly less than x in not plus 1. X in k is strictly less than lambda plus 1 over. Now you know the rest of the proof. No? Up to here is it clear? Now for each k, you have a term x in k, and k's are strictly increasing. Satisfying this condition, you know the limit of this thing is lambda. Limit of this one is also lambda. By Squeeze theorem, this one has a limit and that limit is also lambda. I have to go like this, right? Since I have got everything, I'm going to finish it. Since limit k tends to infinity, lambda minus 2 times 1 over 2 to the k is equal to limit k tends to infinity, lambda plus 1 over 2 to the k is equal to lambda by Squeeze theorem. It's squeeze, give you theorem. X and k converges to lambda. Thus, lambda belongs to Lxn. This completes the proof. I have produced a subsequence of x whose limit is lambda. Therefore, lambda is going to be the lambda belongs to I have written then lambda is the maximum. should write it. Thus, lambda equals max L x. The proof is not the proof. So other side the proof is very similar. Proof is very similar. So I'm not going to write, but you should write it. Lim if xn is equal to Lxn. Same way. Same way. So when I was writing the book, I worked very hard to do this thing. Constructing the sequence, subsequence. Because I was not sure. See the thing is, here we are using very heavily that sup A equals lambda if and only if each simple A belongs to capital A less than or equal to lambda and given any epsilon greater than 0, there exists some A belongs to capital A such that A greater than lambda minus epsilon, and of course A less than or equal to lambda. Again, this convergence of a sequence, when you get L1, idea is this. No, I was thinking, writing the proof, I thought there are elements as limits as close as V1 to lambda. Then if you take any limit, there are terms as close as V1 to that limit, xn terms. Actually that is the proof here. You cannot say, I mean, you have to write like this. So that is the thing. So this is a lot of work when I was proving this. Here in the book, of course, you will buy the book when it is available.
Yeah.
This is very good for you in order to learn. So anyway, now my story is kind of over. I said, so far as he said that Lim Sup in my book style, I have wrote it is a maximum. Lxn has maximum. Actually, according to the book, you can see that it has a minimum too. But of course, I have to show that my definition and his definition are same. Let's see what are the other things I should prove. You don't know.
Yeah. That's it.
Yeah.